In single variable calculus, you'll see that's not a very good integral sign. Maybe I need to practice that. Integral f of x dx, and we want to change the variable. So sometimes I'll write it like f of g of x times g prime of x dx. And this will lead to a new integral. Usually it'll be something like u is equal to g of x, so that du is equal to g prime of x dx. When we rewrite the integral, it just becomes f of u du integral. Now when we make this into multivariable, this is quite harder. I think I've already talked about some other change of variables, mostly spherical and cylindrical. There are infinitely more, depending on how we want to change the variables. In 2 dimensions, we introduce this new we introduce this transformation. X is equal to x u of v. Y is y of u of v. This maps a region into the UV plane into a region R in the XY plane. So we could write we are integrating over this region R. So now we're in this region S, which is using a different coordinate system, and we're not fully done there yet. We're going to have this this is going to be a matrix. This is known as the Jacobian. This Jacobian is going to be written as a matrix of partial derivatives. So for 2 dimensions, it's going to be partial x, partial u, and then you take the determinant, subtract this term from that term. Well, I mean you cross multiply all, but so that's partial x, partial u, partial y, partial v minus partial y, partial u, partial x, partial v. Let's say we're working with polar coordinates. Polar coordinates is 2-dimensional substitution, so you can have x is equal to r cosine theta, y is equal to r sine theta. So we can say x is equal to g r of theta, y is h r theta. So when we find our Jacobian, So we compute each of these partial derivatives and we plug it into the matrix. So if we differentiate x with respect to r, or this term, we get cosine theta. If we differentiate it now with respect to theta, we're going to get, if now we differentiate with respect to theta, we get minus, gotta change, minus r sine theta. Now we differentiate this with respect to r, we get sine theta. And now we differentiate with respect to theta, and that's r cosine theta. When we take the determinant, multiply this term by, now when we cross multiply, we're going to get r cosine squared theta minus r sine squared theta. And this gives us r cosine squared theta plus r sine squared. And these terms are just going to be 1 or r times, that should be pretty obvious, and you just cross that out because that's just equal to 1. So when we change our variables from, when we make this the change from when we make the change and then we add this Jacobian term in polar coordinates, is r dr d theta. And it's because when we took our Jacobian, we're left with just r. When we go to three dimensions, the matrix is now going to be a 3 by 3 matrix, which is a little harder to do. Just a little bit, but so when you do this, you're going to get 9 partial derivatives that you have to compute, and then you will take this term and then, you know, take the determinant. You can decompose it this way, and then you'll take this term and then cross these and get that matrix, and then with the last term you can take that term and then cross these out and have that matrix, and then you'll decompose and have 3 2 by 2 matrices, take those determinants, and then you'll end up with some term that you'll have to multiply by, and that'll be your Jacobian. If we were to use spherical coordinates, if we use these substitutions, x is equal to rho cosine theta sine phi, y is equal to rho sine theta sine phi, z is equal to rho cosine phi. Compute all of these partial derivatives, plug it into the matrix, and take the determinant, we're going to end up with the Jacobian is equal to rho squared sine of phi. So when we plug that into our volume element, dx dy dz is equal to going to be rho squared sine of phi d rho d theta d phi. And that pretty much covers it for change of variables. Maybe in the next video I will do an example. Okay, thanks for watching.